Okay, now we'll talk about regional or intermediate pressure temperature metamorphism, metamorphic zones within regional metamorphism, the index minerals in Barrovian and Buchan metamorphism, contact metamorphism around plutons at high temperatures and sometimes low pressures, and the common mineral assemblages for them. We've seen this diagram before, and I pointed out that the subduction, the high pressure, low temperature trend of subduction zone metamorphism, the high temperature, low pressure trend of contact metamorphism around plutons, and also this sort of intermediate regional metamorphism where it's intermediate between at moderate pressures and temperatures. And I also pointed to these two areas, the Barrovian Scottish Highlands and the Buchan area of Scottish Highlands, as being the original place where the index minerals for regional metamorphism were defined. So we've discussed subduction zone metamorphism. Next on our list is regional orogenic metamorphism. So this is a type of metamorphism associated with convergent plate margins, but not the subducted plate. This is what's taking place in the overriding plate in the subduction zone. This is a dynamic and thermal kind of metamorphism where there could be one or more episodes of orogeny, meaning mountain building or collision, with elevated geothermal gradients along with deformation of the rocks. And the deformation oftentimes leads to foliated rocks that are seen by the layering that forms and during textural changes in metamorphism. So regional metamorphism was really first defined in the Scottish Highlands by Barrow, who studied politic rocks, and these are rocks that have a protolith that is clay-rich, like a shale. So there's a lot of potassium and aluminum in those rocks. And he subdivided the area into a series of metamorphic zones that was each based on the appearance of a new mineral as the metamorphic grade increased. This is Barrow's area, and there is a section along the Scottish coastline where you can walk through each of the different index mineral zones that define Barrovian metamorphism. So Barrovian metamorphism is a kind of regional metamorphism defined by these index minerals. And this is a very unspectacular coastline as far as the geology is concerned. It's very hard to see the index minerals. But as you walk along the beach, you will see chlorite first on the south end of the beach, and then continue north and progressively get into biotite-rich rocks, garnet-rich rocks, and not andalusite actually. That is for the next type of regional metamorphism we'll talk about. Kyanite, then sillimanite. So you're progressing from lower pressures and temperatures to higher pressures and temperatures as you move along his metamorphic zones. So this regional metamorphism, again, is this moderate pressure and temperature kind of metamorphism that's affecting a wide area when continents are colliding. We looked at these metamorphic facies on the last diagram in the last lecture, where we see green schist, amphibolite, granulite facies as the grade increases. And this diagram compares those metamorphic facies to the zones defined by Barrow. So we see chlorite, biotite, garnet, kyanite, sillimanite. And you can see, and this diagram is for a mafic rock, but you'll see the mineralogic changes that take place as grade increases. For instance, in the green schist facies or the chlorite biotite zone, you're seeing K spars, and they start to disappear as you move to higher and higher grade. You see the green minerals, epidote, actinolite, chlorite, that make a green schist green. Those are growing at low grades and then being replaced by different minerals as pressures and temperatures increase. In the amphibolite and garnet, or well, let's compare it to the kyanite and to the sillimanite zones. We're seeing plagioclases and hornblende, which is appropriate for amphibolite facies. And then if it's a palitic rock, you're seeing kyanite and sillimanite. Remember, those are aluminosilicates. And we know that aluminum is not abundant in mafic rocks, and so they aren't represented in this diagram itself. This is simply comparing what these zones are against the metamorphic facies. So with increasing grade, you're moving from rocks that have chlorite into rocks that have biotite, and gradually the chlorite is going to be replaced. And that doesn't mean chlorite disappears immediately when you enter the biotite zone, but it means that by the time you're in the garnet zone, all the chlorite is gone. By the time you're in the kyanite zone, all of your chlorite is certainly gone, and you've got these high-grade minerals growing with the lower-grade minerals. They don't disappear. In the kyanite and sillimanite zone, it's quite common to have garnet. So some minerals persist for a while. Others will become unstable and disappear. It is simply the appearance of a new mineral in a rock that tells you you've crossed over into this next higher metamorphic zone in regionally metamorphosed rocks. Now, Barrow is the Barrovian metamorphism is defined by a trajectory like this, and the zones go from kyanite to sillimanite. That's slightly higher pressure than the neighboring lower pressure regional metamorphic type, which is the Buchan zone. And that's where you see the appearance of andalusite. And so you're moving from rocks that have andalusite into rocks that have sillimanite. And that tells you that they're at lower pressures. And the Buchan area is up here, with the yellow in the andalusite there. So instead of kyanite, you find andalusite in the Buchan zones. And it simply reflects that this area of the Scottish Highlands was never at the same high pressures as Barrow's area down here in the south. So there's a wide range of pressures and temperatures reflected in regionally metamorphosed rocks. And those are all part of this Caledonian orogeny. When Pangaea was assembled, there's this large orogenic belt that basically stitched together North America, Greenland, to Europe and Africa, and created mountain belts that are now, the parts of which are now on different continents. For instance, the Norwegian caledonites here are very similar to the Greenland caledonites. And then Barrow and Buchan's area here in the Scottish Highlands, very similar to what we're seeing in North America along the east coast in the Appalachians. I would be remiss if I didn't point out that we have these regionally metamorphosed rocks as well along the east coast in the Appalachians. So you see the both Barrovian and Buchan metamorphic assemblages reflected in these colors here on the map. And it's not as neat as Barrow's area where you're stepping from one zone to the next, because this area is deformed, and features like this reflect that there was folding taking place, and the fact that you have the lower grade rocks on both sides tells you that there were some tectonics going on. The rocks are deformed, but the metamorphic minerals are there. So this is all taking place in a continental collision zone where you've got a thickening of the crust as you're compressing two plates together. There's, along with this thickening, you see there's folding. And so what happened, the rocks are being deformed, and rocks that were normally mid-crust suddenly can be faulted or folded down until they are residing in a deeper part of an orogenic belt. And it's at these increased pressures and temperatures down deeper where the regional metamorphism is taking place. So we've got this regional metamorphism across a large area at a variety of depths that are recorded in the pressures in those metamorphic minerals. And we've also got plutons developing, and immediately around those plutons we're going to have contact metamorphism taking place at the same time, while this is all separate from the subduction that's ongoing. Now, I don't like the fact that this diagram says that it's low pressure. I say no, I say this is medium pressure and medium temperature metamorphism. And here, the regional metamorphism is being defined by the metamorphic facies rather than Barrow's zones. But you can compare the two. And again, you know, the mineral assemblages that you're seeing here that correspond to the green schist facies with chlorite epidote, albite, or the amphibolite facies with hornblende and plagioclase, that's all going to change depending on the protolith of the rock that you're dealing with. If it's a basalt, you're going to have more iron and magnesium minerals, and if it's a granitic rock, you'll have more feldspars and quartz. So this is an important concept. Metamorphic assemblages are a function of pressure and temperature conditions, very importantly, but also the protolith chemistry. So different protoliths are going to yield different mineral assemblages at the same pressure and temperature conditions. And those protoliths might look like this. You could start off with a very iron and magnesium rich mafic or ultramafic rock, and trace elements like nickel and chrome are going to affect the accessory minerals that you see in the rock. You start off with a shale. That's going to give you those aluminosilicates because it has a lot of aluminum, and a lot of micas because there's a lot of potassium available. If you're starting off with a carbonate protolith, there's a lot of calcium, magnesium, and you'll get some carbonate minerals. If you start off with a sandstone, there's a lot of silica. And if it's a granite, you're having these, these are the elements that are most abundant at the lower end of Bowen's reaction series. So you'll get K-spars, muscovites, quartz, and potassium plagioclases. Contact metamorphism is taking place around those igneous intrusions, and there's a thermal effect of the metamorphic reactions, and there's also potentially metasomatic effects of hot magma intruding into cold, shallow rocks. And metasomatism is when you have fluids flowing through the rocks and causing alteration that way, and potentially changing the chemistry of the rocks as the fluids flow. And these plutons can be at a variety of depths in the crust, and so that means there's a range of pressures that could be present during that metamorphism, and including at very low pressures. And the contact metamorphic rocks are occurring in an aureole surrounding the pluton. This is what it might look like. And the rocks that you get out are going to depend on the protolith. And here is shown a shaly protolith, a limestone, a sandy shale, a sandstone, and the kinds of metamorphic rocks that result from heating from this pluton will depend on the chemistry of what's going in. So in this metamorphic stew, if you add a lot of aluminum and potassium, silica, you're going to end up with phyllosilicates, aluminosilicates. If you are starting off with limestone, which is a calcium carbonate, you're going to end up with a marble, which is also calcium carbonate. If you start off with a sandstone, which has a lot of silica, maybe you'll end up with a quartzite. And the grade of this metamorphism is going to increase toward the pluton, and so you'll get higher temperature phases at places closer to the pluton. So you see Andalusite changing to sillimanite there. And there's also a possible fluid gradient flowing from the pluton into the surrounding rock. So that's going to have an effect as well. And in contact metamorphic rocks, we're dealing with high pressure. We're in the Hornfels facies. And again, the mineral assemblages that you get are going to depend on the protolith. In this case, it's a metabasite. And so what's shown is OPX, CPX, plagioclase, and maybe some quartz. That's going to be different if you've got a shaly protolith to start off with. Okay, what you learned in this module was that about regional metamorphic processes in collision zones, that the Barrovian and Buchan metamorphic zones within these regionally metamorphosed rocks are defined by a set of index minerals that on their appearance defines a new higher grade zone, and that the lower grade minerals can persist for some time. It's simply the appearance of a new phase that is defining that increase in grade. The protolith chemistry is important in determining the assemblage that you're getting in the metamorphic rock that results. And the contact metamorphism is taking place in the aureoles of plutons, so the area immediately surrounding the plutons. And we talked a little bit about the mineral assemblages and how the protolith chemistry is affecting that.